So here is the expression for torque induced in this coil carrying a current I and placed in a uniform magnetic field created by north and south poles. This induced torque depends upon current in the coil, it depends upon the flux density, and also depends upon the construction of the machine. So we want to write it this expression in another form, which will be more convenient when we shall be talking about real AC machines. So what we observe is that current I is flowing in this coil. Current I will be flowing in this direction, and we know that a current carrying conductor has a magnetic field around it. So therefore, due to this current in this coil, a magnetic field will be created. So let's denote that magnetic field and flux density by the loop. The flux density due to magnetic field of current in the loop. What is direction of that magnetic field can be determined by this right hand rule. That is, if we curl the fingers in the direction of current, thumb will indicate the direction of this magnetic field, flux density. So that is perpendicular to the surface of this coil. And this flux density, that depends upon current. More is the current, more will be flux density. It also depends upon the permeability of the path followed by flux lines. So this B is dependent upon current in the coil. It depends upon the permeability, and it also depends upon geometry of the coil. So if here we have a rectangular coil, for the case if we had a circular coil, then it has been calculated that G comes out to be equal to 2 multiplied by R, where R is radius of that circular coil. Over here we can even find G for this rectangular coil using more complex relations. However, we are not interested in determining precise expression for this G. So flux density due to this coil, that depends upon current, geometry of this loop, and upon permeability of the path followed by the flux lines. And from this expression we can see that I, that is equal to G multiplied by D loop over U. We substitute this expression for current into this expression. So this expression becomes torque induced is equal to 2R, I is G B loop over mu multiplied by L and B. This B flux density is due to main magnets, and to differentiate this flux density from this one, we append a subscript S over here, that is magnetic field flux density due to stator magnets, multiplied by sine theta. This 2R multiplied by L, what is that? 2R is this length, L is this length. So 2R multiplied by L is the area of this loop. So this expression is AG or mu B loop BS sine theta. Once the machine, this loop is designed, this A will be a constant, this G, geometry of the loop, will be constant, mu is constant. So let's replace this by a constant K. What was this angle theta? Theta was angle between this force and the radius vector. That is for this conductor's AB, this was situation. This was the radius vector, and force was downwards, F. The angle between R and F was this angle theta. So what is direction of BS? This is direction of BS. this direction, which is perpendicular to this force. So the angle between BS and FAB in this case, that is 90 degrees. What is direction of B loop? We know that direction can be determined by grip rule. If fingers point in the direction of current, then this thumb will indicate the direction of flux density due to this current. That is perpendicular to the surface of this coil. That is in this diagram, what will be the direction of B loop. Here coil is placed like this one. This is coil, and perpendicular to it is the direction of B loop. That is perpendicular to this one, the loop. This angle is 90 degrees. And what we observe is that angle between BS and B loop, that is this angle, is the same as the angle between R and F. That is, this is also equal to theta, because this B loop is perpendicular to R and BS is perpendicular to F. Therefore, the angle between these two vectors is the same as angle between these two vectors. So theta over here, which is originally the angle between these two vectors, is also angle between these two vectors. Therefore, B loop BS sine theta, that is nothing but the cross product of these two vectors, B loop cross BS. So torque induced, this vector, induced torque vector, the direction of this vector was clockwise. This was clockwise. So now question is why I have written it like B loop multiplied by BS, and why not BS cross product of BS and B loop? Why not in this form? Because I should write it in the way such that direction of induced torque remains clockwise. So if B loop cross BS is in clockwise direction into the board, so that is true. However, if I write it in this way, that is not true, because BS cross B loop is in counterclockwise direction. So this expression is not true. Therefore, induced torque, we have an expression for induced torque produced in this coil. This expression will be more convenient when we shall be talking about real AC machines.